A-level specification. Now, when we talk about traversing a graph, what we mean is to visit every node within the graph. And when we say visit every node, we mean to do something with it. So that might be to process its data. It could be to run a process on it if each node in the graph were a machine or a device within a network. It might be that we might look at the data stored within a node and compare it to some sort of search value that we're looking for. Okay, so visiting just means to do something with whatever the node is representing. And there are two different ways of traversing the graph, and these will affect the order with which we visit each node. Now, it's worth pointing out that traversing a graph is different to finding the shortest path through a graph. When we find the shortest path through a graph, we may not explore every single node within the graph along the way. But when we traverse, we do explore every node in the graph. So the two different ways of traversing the graph are depth first, which means we start at a given node and we explore as far as possible along each branch from that starting node before backtracking. And the second option is to do a breadth first search, and this involves looking at the nodes that are closest to the starting node, or whichever node I'm currently looking at, first before progressively exploring further away nodes. And I'm going to talk you through some examples now, showing you each of these in practice along with their pseudocode. So let's start with depth first graph traversal. This is sometimes called depth first search. And this process recursively visits nodes that are adjacent to a given starting node until a node is reached that has no unvisited adjacent nodes. At this point, the algorithm backtracks to the previous node and then goes on to visit any unvisited nodes from that node. And it uses a stack to facilitate this. And there are several uses for depth-first graph traversal, including finding solutions to mazes. So backtracking algorithms are often used to try and look through all of the options in a maze or a Sudoku or something like that. Finding a valid path from one node to another, not necessarily the shortest path, but it will find potentially a valid path. And it's also very useful for determining the order with which processes must occur if they depend upon each other. So, for example, if you're compiling many modules in a computer program where one module depends upon the existence of a previous one, then we can model that using a graph, and we can perform a depth-first traversal, which basically ensures that that a module will be compiled before moving on to the next one that it's connected to. And similarly for any other project management task, like building a house, where we might have to complete certain processes in a certain order. Well, if we were to map all of those processes in a graph, we could use depth-first traversal to ensure that they're all completed in the right sequence. So here we are with some depth-first graph traversal, and what we can see on the screen, if I just select my little laser pointer, is we've got our graph that we're going to be traversing here. We're going to keep a track of the order with which we visit the nodes here. Here we have a stack, which is currently empty, and a stack pointer, which is just pointing at -1 because there's nothing in the stack. And here's our pseudocode, which explains the algorithm. So the first thing we need to do is we need to push a starting node onto the stack. So we're going to traverse our graph from node A as the start, but you could pick any node to start from. We could be starting from D or F, it doesn't matter. And what we do is, having put A onto our stack, we're going to peek that node and call that our current node. So we don't want to pop it because we need it to stay on the stack for now, but we can peek it. Okay, so that becomes our current node that we're currently exploring. And what we do then is we visit that current node, so we add it to our visited nodes list. And remember, visiting means processing, so if this was some sort of data that we needed to run some processing algorithm on, we would do that. If it was a machine that we needed to start up or shut down in a certain order, we might do that. And then for each connected node from the current one, we look at those. Here we've got B and C are both connected. We look at those and we say, are they in the visited nodes list? And if they're not, then we just push them onto the stack. So the first one of those is B. Is it in the visited nodes list? No. So we push it on the stack. And immediately at this point, with B put on that stack, before I've looked at C, we're going to run this algorithm recursively again. So we're going to call depth first, and we're going to pause that iteration or this running of, or this instance of depth first just here. So the green pointer here is our first call to depth first. We're going to start a new call to depth first with this blue pointer. Okay, and you can sort of see A has gone pale yellow now to signify it's kind of historically active, but it's on pause because the new current node now is B. So we're looking at B. So let's visit it. Let's add it to the visited nodes list. And let's look at the nodes it's currently connected to, which is A, D, and E. Let's look at the first of those, which is A. If it's not in the visited nodes list, well, A is in the visited nodes list, so we're not going to push it on. But D was the next one that wasn't. D wasn't, so D can be pushed onto the stack. And lo and behold, we're going to start the process again with D as the new current node and the top of the stack. So we peek the top of the stack, that's our current node, and we visit everything. We visit D, and we look at what D is connected to, which is B and G. Now, B is already in the visited nodes list, but G is not. So let's say if it's not in the visited nodes list, that's G. Let's push it to the stack. Okay, and then again, let's start the process all over again with a new node at the top of the stack. So G is now the one we're going to be exploring. So we visit it, and we say for everything it's connected to, if what it's connected to is not in the visited nodes list, then we're going to add it to the stack. Well, D is already in the visited nodes list, but C is not. Even though C was actually connected to A, we haven't actually visited C yet because remember, A is still on pause exploring B. So actually, C is now going to get added onto the stack by virtue of the fact that it's connected to G. Okay, that gets pushed onto the stack and we start the process again with C at the top of the stack. So we visit C, add it to our visited nodes list, and for everything that C is connected to, A and G, those have both been previously visited. So actually, we're not going to do another recursive call. There's nowhere else to visit. So we pop C off the stack, and that is the first of our finished nodes. We've exhausted C, there's nothing else to see. Which means that this call, this red call to depth first is now going to finish. And execution is going to return to the previous call, the sort of orangey yellow call, where G was top of the stack. G has nowhere else to go and explore either now. So we're going to go back, we're going to check. We looked at C, let's look at D. D is already in the visited nodes list, so nothing to do there, so we can pop G off the stack. We return execution to the exploration of D, and again, D was connected to B and G. Both B and G have now been explored and visited, so we can pop D off the stack, and we return execution to B. B is connected to A, D, and E. Well, we haven't explored E yet. So E now gets pushed onto the stack, and we do a new call to depth first from here. So we pause exploration of B again, the blue one, and let's bring up this purpley one to represent a new call to depth first, and now we're going to be exploring E. E is to be visited, so we add it to the visits nodes list. And let's look at what E is connected to, both B and F. B has been already visited, but F has not. So we're going to add F to the top of the stack, and we're going to run depth first again, this time from F. Okay, hopefully you're seeing the value of the stack in terms of keeping the history of what called us to where. It'd be very difficult to do this process without a stack. So we're visiting F, so F goes on our visited nodes list, and then we look at what F is connected to. F is connected to E, but E's already been explored, so there's nothing to push onto the stack, so we can pop F from the stack. Execution returns to E, or the depth first traversal of E. E has now nowhere else to explore. B and F have both been visited, so E is popped from the stack, and execution returns to B. Remember that B is connected to A, D, and E, all of which have now been explored. So B is popped from the stack, and execution returns to A. A is now the current node again. A is connected to B and C, both of which have been fully explored. So there's nowhere else for A to go, so A is popped from the stack, and we've finished our traversal. Now notice in this process that when we started from A, we went to B, then D, then G, then C, i.e. we kind of went like as far down the chain as we could before we started cycling on ourselves, and then we backtracked, and then we carried on and we went to E to F. So we went as far as we could down this branch, and then we backtracked, and then we finally backtracked to our starting point again. And that's the nature of depth first traversal. You take a node and you explore as deeply from that node as you can until you can't go any further, then you backtrack, and then you go as deeply to any other unexplored nodes. Okay, and that is depth first graph traversal. So you could have a go at programming this using the pseudocode that I've just shown you. Pretty much exactly what you see in the pseudocode can be translated into Python code. So if you want to pause and have a go at that now, and when you return to this video, I'll actually show you an implementation that I've put together, which hopefully will be similar to yours. Okay, so here is my implementation of the depth first traversal. I'm using a stack that I've already written and imported from a separate file, so it's a pretty standard implementation of a statically sized stack, so it has a maximum size. We have our push methods, pop methods, peek, is full, is empty tests, and we're importing and using that. I've got the graph represented as an adjacency list using a dictionary, so A is connected to B and C, B is connected to A, D, and E, and so on. I've got an empty list that's going to be used to store the visited nodes. We've got our stack, which can store up to 7 items because there's 7 items in the graph. And then we've got the depth first traversal algorithm itself. So just like the pseudocode, what we do is we work out, well, what's the current node? Well, to get that, we peek the top of the stack. We append the current node to our visited nodes list. And then we say for every connected node, for every node that is in graph current node, bearing in mind that graph is this object, it's a dictionary, so we drop the current node in. If it were A, it would return the list containing B and C. So we can then iterate through B and C, so connected is going to be B and then C. If the connected node is not in the visited nodes list, then we push the connected node onto the stack and we start the process all over again. Once we return back to depth first traversal, and once we've explored our connected node, the for loop will continue for any other nodes that it's connected to which are not in the visited list. And eventually, once we've exhausted all of those, we then pop we can just pop the currently explored node, which is the top of the stack, from the node stack. Okay, and then to call this, we simply need to push our starting node onto the stack, and then we just run depth first traversal, and to prove it's worked at the end, we'll just print out the visited nodes list. So if we run this, you see that we've visited A, then B, then D, then G, then C, then E, then F, which is the same order as the pseudocode that I've shown you, or the worked example that I've shown you. It is a different order to if you'd followed the instructions on this slide, which was to say to actually implement this particular graph, because I haven't implemented this graph. So if you've implemented this graph, you will have a different output. But if you use the graph shown in these slides, then you should have the same output. Now, the eagle-eyed amongst you may notice that there was a function I've hidden called simpler depth-first traversal, and this is basically exactly the same, but it doesn't use a stack explicitly. So all we do is we take a node, which we'll call our starting node or our current node, we visit it, and then we look at its connected nodes. If our connected nodes have not been visited already, we just for each of those connected nodes, we just run the process again on the first of the connected nodes to the current node, if that makes sense. In the background, it is still doing exactly the same thing. Because it's a recursive function call, and any function call gets placed onto the call stack, and each stack frame within the call stack retains the current state of the stack, it is still using a stack, and it does exactly the same thing. And just to prove that, let's call it instead. So this is just simpler depth first traversal starting at point A. If I run, we get exactly the same result at the end. Okay, so I mean, this just demonstrates how elegant and simple the depth first traversal algorithm actually is. It's just a few lines, a really nice simple process. Okay, so we've looked at depth first traversal. Now let's consider breadth first graph traversal. So with breadth first traversal, we add all of the nodes that are adjacent to the current node to a queue of nodes to visit. And then we use iteration rather than recursion. We use iteration to repeat this process, always taking from the front of the queue. So depth first uses recursion and a stack. Breadth first uses iteration and a queue. And it has many uses as well, just like depth first, it has specific uses. So these include identifying friends and first degree contacts within social networks. Think about it, if you're trying to work out who are your friends in a social network, you don't want to go to your friend and then go to their friend and then their friend and then their friend and their friend with a depth first traversal, because A, those people are not your friends, and B, you'll probably never get to the end of it because there's about 6 billion people to traverse. Whereas actually, if you're just trying to find your immediate friends, you want to find all the ones that you are directly connected to first, before finding out who they are directly connected to. So identifying friends in social networks, identifying immediately connected devices and networks within a computer network. So for example, finding out for a router, it might want to find out what devices and what other routers it is connected to. Crawling web pages. If you ever do a web crawler, if you're a search engine or you're scraping web pages, you want to build an index of links from the current page, then you're going to want to do a breadth first traversal. Again, if you did a depth first traversal, all that would happen is you go from the current page to the first of its connected pages, and then to another connected page, and another connected page, and another connected page, and you would never actually get to the end of it. Well, you would eventually, but you'd have to scour the entire World Wide Web first. Finding a valid path between two nodes within an unweighted graph. This sort of makes more sense when you look at Dijkstra's shortest path algorithm, which is a breadth first traversal algorithm that finds the shortest path between two nodes, and that uses a modified priority queue rather than just a let me visit this queue. It visits based on priority, and priority is given to the lowest weightings between two nodes. That's sort of for another day, but it's worth you knowing. If you're in an exam and you're asked to give a use of a breadth-first graph traversal, it's perfectly okay for you to say you can use breadth-first graph traversal to find a valid path between two nodes in an unweighted graph. But if you don't write the word unweighted, don't expect to get a mark. So let's look at this algorithm. Here we go. We've got our graph again, just like before. And instead of a stack, this time we've got a to visit queue. So this is a queue of the nodes we're going to be visiting. And we've still got our list showing the nodes we did visit in the order we visited them. So we begin by enqueuing the first starting node to the queue. So we're going to drop A. Again, we're going to start at A, and we're going to drop that into our at the beginning of the queue. And while this queue is not empty, and that's key, while the queue is not empty, let's dequeue the first item from the queue. Let's take A and let's explore it. So A is our currently exploring node. And what we need to do is we visit that node, so we add it to the visited nodes list, and then we look at each of the connected nodes. So for each node that we are connected to, which are B and C in this case, if a connected node is not in the to visit queue already, and it's not in the visited nodes list, so basically we haven't already been there and we aren't planning to go there in the future, then we enqueue it and add it to the to visit queue. So we're going to add B and C because both B and C are connected to A. They haven't been explored and we don't have any plans to explore them up till now. So we add them to that queue. Okay, and then we can finish our for loop because we've finished thinking about the connected nodes that we need to add, and so now we can carry on. We can dequeue the next item for our to visit queue, and we can go and explore it. So again, is this queue empty? No, it's not. So let's dequeue the B. B has now got the focus. Okay, so we're going to visit B, so it goes into our visited nodes list. And then we say for every node connected to B, which is A, D, and E, if it's not in the visited nodes list and it's not in a queue of nodes to visit, then we add it to the queue. So in this case, A has already been visited, but D and E haven't, and we don't have plans to visit them yet. So let's add those to the queue, and let's repeat the process again because the queue's not empty. So next we're going to visit C. So we add C to our visited nodes list, and we look at everything that C is connected to, which is A and G. Now, A has been visited already, G has not, and we don't currently have plans to visit it, so we add it by enqueuing it onto the to visit queue. Okay. We're finished with C, so let's go, let's dequeue the next item from the queue, which is D, and again we repeat the process. So we visit D. D is connected to B and G. Now it's an interesting one. B's already been visited. G is in the queue to visit. So there's actually nothing new. We're not discovering any new nodes that are attached to D. So there's nothing to do with D. We're absolutely finished, so we can just move on to the next item in the queue, which is E. So E is connected to, so E is our new node, so we visit E. We look at what E is connected to, which is B and F. B has already been visited. F hasn't, and F isn't in the to visit queue, so we can add F to the queue, and we're finished with E. So let's dequeue the next item, which is now G. G is the current node now, so we visit G, add it to our visited nodes list, and we look at what G is connected to, which is C and D. Both C and D have been visited, so there is no need to add them. Again, we're not going to learn anything new. There are no new nodes to discover. So we're finished with G, and we carry on. We dequeue the next item from the queue, which is F. So we visit F. We add F to our visited nodes queue, and we look at what it's connected to. It's connected to E. E has already been visited. It's not connected to anything else. So we're finished with F. The queue is now going to be empty. So notice our iteration is while to visit is not empty. Well, it is empty, so we drop to the end of our while loop and we can end our procedure, and we're finished, we're done, and that is now our graph fully traversed. And the order of traversal this time was A, B, C, D, E, G, and F. So again, let's do a programming task again. Let's implement, this is a new graph on the right, this is a different graph, so try implementing this graph. And write a breadth first traversal to traverse this graph from point A. Okay, and don't forget you should output the order with which each node is visited. Now if you want to go away and have a go at that, pause the video, come back in a moment, and I will show you my solution to this. Okay, so here is my implementation of a breadth first traversal. Again, we're importing a queue object here, which we're going to be using. So we've got a queue, we've got our graph set up as a dictionary, and here's the algorithm. We need to get, when we start, we need to declare a nodes to visit queue, and we need a visited nodes list. Just realised I haven't given a size to my queue, so let's make it size 7 again. 1, 2, 3, 4, 5, 6. Oh, it's actually only 6 items in this queue, so that's fine. 6 will do. We've got our visited nodes list, and we've got we're going to begin by taking some sort of starting node which we're given when we run the algorithm, and we're given a graph. So we're going to take the starting node and we're going to enqueue it. Okay. Then we say while not nodes to visit is empty. So while the queue isn't empty, take the current node by dequeuing from the front of the nodes to visit queue, append that node to our visited nodes list, get all the adjacent nodes to the current node, and for n node in adjacents, if that node is not in the visited nodes list and is not in the nodes to visit queue, and I've got a special method in my queue to determine if an item is in the queue or not, which we kind of need to use for this. Then if it's not already in the visited node and it's not already queued up, then we simply enqueue that adjacent node. Okay, and that's just going to repeat for all of the adjacent nodes, and then that entire process is going to repeat while we have items still in the nodes to visit queue. As soon as the nodes to visit queue is empty, we return our list of visited nodes, and we can then, when we call this breadth first traversal algorithm, we can print the result of calling it, which is going to print the list of visited nodes. So we're going to perform this now on the graph, starting at node A. So let's run, and we got an error. Fantastic. That's because okay, that was because I made a modification to my queue and I was actually just appending things on the end of a list rather than having a fixed size. So don't worry about that. That was the queue implementation that let things down. So here we are. We're running now, and we've got the output order A, B, D, F, C, and E. And notice we can pick any nodes to traverse from. So if we wanted to start at, say, node F, we would get a different order. We'd start at F, then we'd explore A, B, D, C, and E. Or we could start at E. And again, we'll get a different order depending on what E is immediately connected to. Okay. So very, very, very much along the lines of the pseudocode. As you'll see again, it's not a complicated algorithm. Because we're using a queue, we just iterate through and we just keep doing it until the queue's empty. Every time we find a node we haven't already explored or we're not planning to explore, we just add it to our queue and we just carry on until we have seen and visited every one of our nodes. So there you have it, traversing a graph using depth first and breadth first algorithms. I hope you found that useful, and the best thing to do to get your head around this is just to draw some graphs out on paper and just apply each algorithm and just practice having a go at each traversal, maybe with a friend, and compare the results and just check that you're both getting the same answers each time.